back to. Okay. So let me do a quick dictionary between the surface setting and the free group setting, and then I'll talk more in detail about the surface setting to motivate our work in free groups. So on one side, we are thinking of hyperbolic surfaces. And let's just think of closed-oriented hyperbolic surfaces for this talk. So these are genus at least 2 surfaces. And the parallel is, so I guess I should say, fundamental group of hyperbolic surfaces. And on the other side, I'm thinking of free groups, which I think of as fundamental group of like wedge of n circles. Also, if I'm thinking of, so let's say this is free group Fn, if I'm thinking of even rank, then this group is also, or the fundamental group of a surface with one boundary is also a free group. So often we think of surfaces of this type to think about free groups as well. Here we have the mapping class group, which is the group of orientation preserving homeomorphisms up to isotopy. So let me just write equivalence for here. And the corresponding group here is what is called the group of outer automorphisms. And that group is the group of automorphisms, but then I quotient out by inner automorphisms. The inner automorphisms are exactly the ones which are conjugations. So you conjugate everything by one particular element. Yes. Then on this side, we have Teichmuller space. So mapping class group acts properly on this space. And basically what are points in this space? They are marked hyperbolic metrics, again, up to some equivalence, but they are basically hyperbolic metrics marked hyperbolic metrics on the genus G surface. On this side, we have something called outer space, defined by Culler and Vogtmann. So here I was talking about marked metrics on that hyperbolic surface. Here I want to talk about, so let's see, I want to talk about graphs whose fundamental group, so let's say I'm talking about F2, whose fundamental group is F2. So I'm thinking of, let's say, this graph, or maybe this graph, and I don't want vertices of valence 1 or 2. So I have these graphs, they are marked. So basically, let's say my free group is, let's say, generated by A and B. Then I have to give you a marking. Basically, I have to tell you how is the fundamental group of this row's free group of rank 2. So one would be, okay, this loop is A, this loop is B. Another way would be this loop is AB and this is B. Or to read the loop A in this graph, I have to do the first loop and then the inverse of the second loop. So that's a marking and some metric. And usually we think of volume 1 metric. So there are some lengths assigned. I should probably draw some marking here as well. So here I'm thinking this is loop A and this is loop B. And again, there is some equivalence on these graphs, but let me not say what that is. And often so either you can think of points in the space as these marked metric graphs of volume 1. Or if I think of the universal cover of these graphs, I get trees, and then I have the free group acting on trees. So free group acting on, so I can think of points as metric simplicial trees with the free group acting freely and minimally. So if you don't know what these words mean, just think of universal cover of these guys are. Thank you. So these two spaces will play a role in what I'm talking about. So basically, eventually I'll be looking for limit sets. I'll be looking for paths at paths in this space, and I want to understand their limit sets in the boundary of the space. Some other objects that will show up will be, so I'll talk about curve complex. So Babak defined it last week. And there is another complex here. So this space is delta hyperbolic. There is another complex here, which I'll not define, but let me just write the name, which is also chroma of hyperbolic. The key object here will be laminations or foliations. So in this talk, I'll talk about laminations, but if you're familiar with foliations, you can think of both, but I'll stick to talking about laminations. And the corresponding object I want to talk about here is trees with some kind of nice pre-group action. And then we'll have, so what kind of paths am I talking about? Here I'll talk about Teichmuller geodesics, which I guess you think of them as given a quadratic differential and a point, and then you like flow, move along that point. And here I'll give an example of something called folding or unfolding path. So folding, so basically outer space, there's a metric on it, but that's not symmetric. So usually you have like some kind of asymmetry in your paths. So you have like these folding paths are basically like forward geodesics, and these unfolding paths are not geodesics, but they are like backward paths. And I'll do an example later. But then the limit sets behave differently. Okay. So just some dictionary, but let's move on to let's go back to the surface case. So let me explain. Basically now what I'm getting at is limit sets of geodesics in Teichmuller space. So that's the story I want to tell at first. So I'll remind you what the curve complex is. So S is my closed orientable surface of genus at least 2. Let's, as Babak did, let me just define the graph. The vertices are homotopy classes of essential simple closed curves. So simple means no self-intersections. Essential means not homotopic to a point. So here are some examples. Let's say alpha, beta, gamma. So I've drawn some essential simple closed curves, and edges are given by disjointness. So two vertices are joined by an edge if they don't intersect. So this space is famous result of Mazur and Minsky, that this space is delta hyperbolic. Now, so let's say I'm in the space, the curve complex, and let's say I take a path. I don't know why I'm drawing it like this. but let's say I take a path alpha 0, alpha 1, alpha 2, and so on, going off to infinity. It's a hyperbolic space, and I can think of this path going off to infinity. When I say that this path is going off to infinity, so these alpha n's, because it's going off to infinity, it can't be disjoint from any simple closed curve. So it's basically these alpha n's are intersecting more and more closed curves on my surface. So somehow in the limit, like I'm trying to understand the limiting object, and the limiting object will be something which intersects every simple closed curve. And these will be, so these will be some kind of laminations. So the boundary here, these are called ending laminations or minimal filling laminations. Yes, yeah, that's the next thing. So I'll define lamination, minimal filling, and we'll do some examples. So what is a lamination? So to define this, let me first fix some hyperbolic metric on my surface. So a geodesic lamination, L is a closed subset of the surface. That is a disjoint union of simple, complete geodesics in X. So I will use this. No, I decided I'll stick to 2 words. I think I'll stick to my. What? So I'm looking for closed subsets of my surface that are a disjoint union of simple complete geodesics. So can you think of an example? Right, just one simple closed curve. That's an example. So let's draw. Let's say this alpha. So that's a simple closed curve. It's a closed subset. This is just a simple complete geodesic. So that's an example of a lamination. I can draw a disjoint union of 3 simple closed curves. That's a lamination. Let me draw something. So let's say I have this geodesic. What I'm trying to draw here is it's just like a, it's wrapping around that part like infinitely often. It's a infinite on both ends. It's just wrapping around. So this is a simple complete geodesic, but it's not closed. This set by itself is not closed. So to make it closed, I have to introduce these 2 curves. And then the union of these 3 geodesics, that's the lamination in this example. And I can draw a crazy looking picture. Let's see if I can. This is Thurston's picture of what a generic lamination looks like. So you see this, now let me draw the full picture. You see some complementary regions or like a triangle here. So like you see some contractible complementary regions. This is just for entertainment, I guess.
There are no closed curves.
Yeah, here there are no closed curves. and every leaf will be dense in the lamination. Okay. Okay, so that's lamination. What is filling? L is filling if the complement in the surface is a disjoint union of disks. So I guess none of these are, this is not filling, this is not filling. And I'm trying to draw a filling one here. And L is minimal if every leaf of L is dense in L. So here there's only one leaf and it is dense in itself. So this is minimal. This is not minimal. The closure of this white leaf is the whole lamination, but the red leaves are not, their closure is not the whole lamination. So this is not minimal. And again here, I was trying to draw something minimal. Okay. Say that again. The endpoints lie on a Cantor set of this one. I think so. Is that right? Or
so with some proviso, so basically if you take a transfer,
right, those are Cantor sets. Like if I
now related to the universal cover every point is going to have a solve. So if you take a transversal and put it out to infinity,
then yes. Okay. Right. Okay. So we so the boundary of the curve complex are these minimal filling laminations, but I'm eventually interested in the boundary of Teichmuller space. Because remember, I want limit sets of geodesics in Teichmuller space. So to define that, let me put measures on these laminations. Let me define measured laminations. Okay, so our transverse measure mu on a geodesic lamination L is a collection of finite non-negative measures I shouldn't have pushed, okay. Non-negative measures on the transverse arcs to L such that, so there are three things. So let me just draw, let's say this is my lamination L, and let's say I draw a transverse arc alpha. So I want to assign some measure to every arc that is transverse to my lamination. And I want this measure to be invariant under, it's called projection under the projection along the leaves, or if I move alpha along the leaves such that it stays transverse, then let's say this is alpha prime, and alpha prime should have the same measure if I'm just flowing along the leaves. So that's the first thing. The second thing is it should be consistent with restriction. So if I take, let's say this has some measure, if I take a smaller sub arc, that should, like the measure on the big one should restrict to the measure on the small arc. And the last thing is that the measure is only counted when you intersect the lamination. So basically, if I draw some arc which does not intersect my lamination, then it should get measure 0. Yeah, I want that picture, so let me just push this up. Okay, so let's think about some measures on these pictures. So here, if let's say this is my, okay, shouldn't call it, okay, let's say my transverse arc is A. No, call this alpha. Let's call this A. Okay, so the measure I want to define on this is counting measure. I just want to count how many times alpha intersects A. So let's call it mu sub A of alpha is basically alpha intersect A. This is the counting measure. And if you like universal cover, then you can think, okay, I have the universal cover of the surface. I lift this curve A to the universal cover. I get lots of flips of A, disjoint flips of A. This arc alpha, it gives me some. I should draw a picture. I don't know why I'm waving my hand. So another way to view these is, so let's say this is A, and I get some lifts of A, and then I have my transverse arc alpha, or alpha tilde, I guess I should say. So this gives me some set in the boundary, like some double sets, like U cross V, and I just count how many lists of A are hitting that set. One can also think of, so if you've heard the word geodesic currents, this is how one thinks of geodesic currents, but not going to use this for this talk. Okay, so this is a counting measure. And this is the only, up to scaling, this is the only measure I can put. Given all those conditions, this is the only measure I can put on this lamination. Here, let's say this is A, B, and C. So I can put a measure, mu sub A, which counts how many times I intersect A, but let's say it doesn't count B and C. Let me call that mu A. Here, I can have mu B, mu C. So mu B only sees B, only sees intersections with B, but nothing else. Okay, these are three things, but I can also take linear combinations of these, of all three. So projectively, I'm just drawing these pictures up to scaling. I get this 2 simplex. In this example, this is slightly more interesting. And maybe you can think, so let's say this is A, B, and C. I claim that C cannot have any positive measure on it. You will run into problems because of this infinite winding. So here I will just get this 1 simplex. And here I was trying to draw, let's say this is I was trying to draw something which has only 1 measure. These are, let's say this is the lamination associated to a pseudo-Nosov homeomorphism. So then I will just have 1 measure on it. Okay. Oh, and then a lamination is called a measured lamination. A geodesic lamination is called a measured lamination if it has a transverse measure on it. Okay. So let's say this is, so imagine the foliation, let's say the stable foliation of a pseudo-Nosov homeomorphism, and whatever way I can get the corresponding lamination. So let's say this is that lamination, the one corresponding to pseudo-loss of homeomorphism. Then those are, I'm going to define the word uniquely ergodic, but those are uniquely ergodic. Yeah.
So basically, these are piecewise flat structures on the surface, so that come with the x-axis and the y-axis. So lengths of the x-axis would be the roughness measure on the y-axis.
Okay. So I use the word uniquely ergodic. Let me define it. So I say a lamination, a geodesic lamination is uniquely ergodic if it supports exactly one transverse measure up to scaling. So in our examples, this is uniquely ergodic because there is only one transverse measure. This one is non-uniquely ergodic because you got big simplex. And this one. Yeah, that's why I'm saying, let's say pseudo-Nassau. Let me put that word pseudo-Nassau here. That's the example I had in mind. Okay, so now here's a question, or first an observation. If I have, let's say L is uniquely ergodic, then this implies that the lamination is minimal. So minimal means every leaf is dense in L. Because if it was not minimal, then I will have I have two leaves which are not dense with their closures, and I can put two different measures on their closures. That will not be uniquely ergodic. What about the reverse implication? If I start with a minimal lamination, should the lamination be uniquely ergodic? So so every leaf is dense in the lamination, but can I still put two different measures on it? With mutually singular support. So the first time I heard of this, I think it blew my mind because I was like, every leaf is dense, but I can still put two measures with singular supports. And singular supports, I guess, means disjoint supports and some. No, support is we take the closure, but I can break the whole space into disjoint union of two things, blah, blah, blah. So hopefully you agree with me that this is a interesting, non-trivial question. If you have something minimal, is it uniquely ergodic or not? And it's not a new question. People were curious about it a long time ago. So in the, I think, late 60s and 70s, so I'll just say the names instead of writing them. Veach, Sataev, Keynes, Newton, Keene, Mazur. So they came up with examples of laminations, or they were working in the setting of foliations, which were minimal but not uniquely ergodic. So let me just write down. Sorry? There exists non-uniquely ergodic minimal foliations or laminations. Let me say foliations because the original and these original examples were coming from interval exchange transformations, so very dynamical objects. Mazur's work was doing rational billiards on translation surfaces of flat surfaces. Then I think I don't know what that is. I don't think so. Yes. One construction here was take two torus, genus 1 surfaces, make a slit in them, then glue them together, but then choose your direction of flow such that there are some number theoretic conditions on what direction you're flowing and what's the length of the slit, which will give you that you'll end up spending more time in one side than the other, something like that. This is like very vaguely what goes on. Yeah, so these are some of these interval exchange transformation or things are some things I want to understand. The construction that I do understand is due to Gabay, which is more topological. So he also constructs these non-uniquely ergodic.
This question is what distinguishes topological dynamics is bounded from.
Yes, yeah, the topology and like this is a topological thing and this is a dynamical thing. So Gabay's construction is topological. He starts in the curve complex, takes two curves that are disjoint, and then does something with them. I don't know if I will have time to talk about it, but I had to decide whether to just do that or go to outer space eventually. Okay. So this is, I think this is super cool. Okay, so again, going back to our goal. So we defined laminations and we saw these minimal filling laminations as boundary of curve complex. And then we defined measured laminations. And we did that because there is a Thurston compactification of Teichmuller space, which is the space of projective measured laminations. So measured laminations, but you look at them projectively. And maybe I'll just write here a record. This is, these are the minimal filling. Laminations. Okay, and then what's our goal? To understand limit sets of geodesics in Teichmuller space. So I'll tell you a few results about this. So the first one is due to Maser. So I guess I'll say words that I haven't defined, but maybe that's okay. So I want to take a Teichmuller geodesic in Teichmuller space. So this is usually given by a quadratic differential. And this quadratic differential has a vertical foliation associated to it. And I guess you should think I have this vertical foliation and I'm like stretching or something along that foliation to move in Teichmuller space. So Maser showed that if this vertical foliation associated to this quadratic differential is uniquely ergodic, then this geodesic does converge to a point. In the boundary of so I'm talking about Teichmuller metric on my space, but I'm thinking of the Thurston compactification. Okay, so Maser says that if this vertical foliation is uniquely ergodic, then you always converge to a point. So then the question is, does every geodesic converge to a single point in Teichmuller space? And it would be boring if it did. So Anya Lenzen showed that it need not. So she constructed an example of a Teichmuller geodesic whose limit set is a one simplex in PML. So when I say it's a one simplex in PML, it's basically there is a lamination whose one simplex of measures, so that lamination is not uniquely ergodic, and it has a one simplex of measures on it. And this geodesic she constructs converges to that whole one simplex. No, so in her example, it's not. Yeah. Her example is not minimal. But Leininger, Lenzen, and Rafi, they constructed examples of Teichmuller geodesics converging to the full one simplex, which were minimal and filling. So Teichmuller geodesic, one simplex, and minimal filling. So this example is a very specific example. This is 5-punctured sphere. Yeah, 5-punctured sphere. The previous one, I don't know. I think Babak knows better. Genus 2? Okay. There, the Teichmuller space is hyperbolic space. So yeah, there we don't have the sphere. Yeah. So okay, I will come back to this result, because this is what we this is the analog of this is what we prove with Besvina and Jingtao. There's a result of Chaika, Maser, and Wolf. So Chaika, Maser, and Wolf. They construct Teichmuller geodesic, but then they show that the limit set need not be the full simplex. It can be a subset of the simplex corresponding to a measured lamination. I should not pick the big charts. Subset of. And then Babak has a lot of work along these similar directions with co-authors. So let me mention some of it. So with Brock in multiple papers. So they produce examples of Teichmuller geodesics whose limit set is not even simply connected. The limit set, it turns out to be a circle. And then maybe I'll mention one more result. So this is Lenzen, Babak, and Rafi, where they construct Teichmuller geodesic. So all these examples that I was writing, they were all like one simplices. So they construct examples which are d-dimensional simplices. So you can have limit sets which are higher dimension, and this is also not minimal. And I think this last construction is gluing multiple tori together along slits. I see. But you can do it for D, right? I didn't misread it. Okay. But then they also study, so these results are all about Teichmuller geodesics, but you can put Weil Petersson metric on Teichmuller space. Again, what Babak talked about last time. So they also study what happens to Weil Petersson geodesics. Like if I take those geodesics, but still look for limit sets in the Thurston boundary, then how do they look like? Do they have similar behavior or not? And so for Weil Petersson, I think they have examples where the limit set is a circle, and they also have examples where it's one-dimensional. And I think this one is minimal, this one is not minimal. Okay. And Maser, yeah. So I guess what I'm trying to say is that there's like lots of weird things are happening. So let me So I want to write down the second result in more detail because our theorem is a direct analog of it. And then I will explain a few more terms. I want to say what a folding path is very quickly, and then I can state our result. So they say that for a sequence of numbers, they construct a sequence of simple closed curves. My Rn of simple closed curves on 5-fold sphere. Such that, and it's an explicit sequence, like I can tell you what that sequence is. So the first part is there exists an R such that if these Ri's are bigger than this capital R, then this sequence is a quasi-geodesic in the curve complex. So say this is the curve complex. So I have a sequence of these curves, and they prove if these coefficients, if these R sub i's are big enough, then you get a quasi-geodesic, which is converging to a point at infinity, and that point at infinity is a minimal filling lamination. Is there a question?
So it's basically saying that for two pairs on a subsurface, the projection is large.
Yes. Yes. Yeah. Yeah. These Ri's are exactly the projection of this guy and this guy on this guy, the middle guy. And then they show that if these R sub i's grow fast enough, so I'm not saying they quantify it, then this lamination is not uniquely ergodic, non-uniquely ergodic. And finally, they show that there exists a Teichmuller geodesic way. So there is a map from Teichmuller space to the curve complex, which if you take a point X, you look at the shortest curve, then you map it down. So they say there exists a geodesic ray whose projection is this quasi-geodesic that we built, and whose limit set is, let me just write, the full simplex of measures on lambda, which turns, in this example, turns out to be like this one simplex. Any questions? So you should think of these coefficients. In Babak's talk, he was talking about these like continued fractions which were telling you whether your geodesic was staying in compact part. And there is, like, I'm not talking about compact parts anymore, but you should still think of these, the sequence of numbers R sub I as, let's say, some continued fraction thing for data for this lamination lambda. So if these coefficients are big enough, then this lamination is non-nuclear Gotic. That's like the first. That's the first thing.
Is there
Like the continued fraction thing?
Yeah.
I don't know anything more than like the first thing Babak mentioned the other day. Yeah.
the goal of this growth function?
Yeah. Right. Right. Yeah. Yeah. So actually, like Jing, who's my co-author, she would keep saying that these, for our case, we also have these numbers, and she would say, oh, these are like, one can think of these as continued fraction approximations of things. And I think that I didn't quite understand that when she would say. So Babak's talk was helpful for me because I saw that thing in his talk.
Serious.
Yeah, I found that paper. Yeah. So this is basically roughly like, at least in our case, this is like if the difference between these RIs is going to infinity.
What is there? What would they mean by RI goes constant?
I don't remember what they say. Like this sequence.
Next to the next chapter. Then neighbor,
Yeah, in outer space, somehow like these two sequences, like you can associate matrices and then they both end up converging to different points. Yeah, it boils down to a lot of linear algebra in the outer space case. Hmm. Yeah. So let me just quickly say, at least draw an example of a path in outer space. And then I will tell you how our theorem is, what's the result in the free group setting. Okay. So for us, we have outer space. So that's like Culler-Vogtmann outer space. And recall the points in the space are these, what were they? Metric simplicial trees on which the free group was acting, right? These were graphs, and like I said, you can think of the universal cover. These are metric simplicial trees on which outer space is acting. In the boundary, you get more trees, but those trees need not be simplicial anymore. But the free group is still acting on those trees, and like they have properties, it's called very small, but whatever, some trees, and they are R trees. Okay, for like, let's just, yeah. One example of something in the boundary is basically start with a surface Yeah, so let me just give you an example of a tree in the boundary. Okay, this is highly non-generic example, but let me still give you this example. So start with this surface, its fundamental group is free. Start with a lamination on this surface. So, and let's say let's first start with a simple lamination. If I draw the universal cover, I draw the lips. I can draw a dual tree. I give myself a vertex for each complementary component. And if they're adjacent, I draw them, I connect them by an edge. So that's a way of associating a tree to this lamination. And if you know the words bus, and this tree, the fundamental group is acting. So I have a tree on which the free group is acting. Here it's still a simplicial tree. Okay, but if I take a complicated lamination on this tree, sorry, on this surface, let's say one of my laminations for a pseudo-NASA. So here every leaf is dense in the whole lamination. And let's say I want to do the same construction upstairs. So now the picture is like more complicated. It's not as simple as this. As we were saying, like each cross section is a Cantor set. But I want to do the same thing. I want to give myself vertices for, now they will not be vertices, but like points for each complementary component, and I want to join them. And what I'll end up getting will be like a very hairy tree. At every point I'll have like branches sticking out. So those are highly non-generic examples of trees in this boundary. But this is I think this is the only one I can sort of. Yeah, sorry, I forgot to say. Yeah, there is a transverse measure on this lamination, and I use that measure. Like, let's say this was just 1. So this edge will have length 1. And here, whatever measure it has, I will use that, yeah. But again, these are not the typical examples in this boundary. Okay, maybe. Yeah, I think I don't have time to like do an example of a geodesic, but so I'll just repeat something I said earlier. This space has a metric which is not symmetric. So like to go from point A to point B, and then from point B to point A back, you get different distances and geodesics. So to go from point A to point B, a particular kind of geodesic is something called a folding path. Let's say there's a very concrete geometric way of defining these folding paths. And it's a fact that these folding paths always have a unique limit point. So from the perspective of studying limit sets in this space, these folding paths are actually boring because I always know they will converge to a point. But something called unfolding path is basically, so paths in outer space always have a direction. I'm always facing something. These unfolding paths are basically me facing this direction, but just walking backwards. And when I'm walking backwards, I don't know what I'm seeing, and I might end up getting weird behavior. So for these unfolding paths, so let's see, how should I draw it? So my arrows are still pointing forward, but I'm going backwards. And we basically produce an example. So I think now I can edit this. So for us, we also like come up with a sequence of, now we construct 3 factors. So I'm just drawing an analog here. This is something called the 3-factor complex. The vertices here are 3 factors. One way to think of this is like these, not every curve gives me an element in the free group. Some of those are primitive, and those will be like the 3 factors. There's more here. And there is similar machinery of like a map here, and then projections are well defined. 3 factors of proper 3 factors. The edge group, sorry, the edges. The edges are containment. Here they are containment. Or let me just say, vertices are rank 1 free factors. So then I'm really thinking primitive curves here, and 2 are joined by an edge if they are elliptic in the same splitting. Our example, we work in free group of rank 7. So then we consider, so like we find these numbers such that our sequence of free factors downstairs converges to a point in the boundary, and the boundary here, instead of laminations, I get trees. And so these laminations, minimal filling laminations, are sometimes also called irrational laminations. And these trees, these are irrational trees, again, some properties. I think at this point, I'm just like building analogy and not really defining anything. Sorry? Yeah. And then we say that this tree, this limiting tree, is non-uniquely ergodic. So maybe to see what it means for a tree to be non-uniquely ergodic, in this example, if the lamination has multiple measures on it, the tree will also have multiple measures on it. Length functions, yeah, sorry, length functions. Yeah, artery structures, yeah. So we can get these, this tree to be non-uniquely ergodic in that sense.
Say, underlying topological tree.
Right.
And there will be a homomorphism from the tree to the tree, conjugating the first group action to the second group action. A, B, the actions are by isometry from the group trees, but the length functions are not proportional.
Right. Also, I should say, like, it's a little tricky for these things. You only get homeomorphism in observer's topology, not in the metric topology necessarily. Okay, and then yeah. So for unfolding is basically like I have my point, and then from here I'll draw a folding path. Then from like further back, I'll draw another folding path, which is compatible with the first one. So they're going off to infinity.
Yes, the folding path is one whose reverse the folding path. One for which the reverse orientation you get a folding path of any subsegment. Correct?
That same subsegment might not be the folding path, like if you go the other direction, I think.
So, what I'm saying is that suppose you have here this. Yeah, so A, B, hello, is an unfolding path, A, B, A is an unfolding path.
So let's see. So let's say this is like, so these tau i's are graphs in outer space, and there is a map from tau 1 to tau 0, which basically tells me how to fold from this guy to this guy. And then unfolding path would be.
The sequence of.
Yes. Yeah. And I was just saying that if I draw folding path from this guy to this guy, that might be something else. Okay. Yeah.
I would say that tau 1 to tau 0, sorry, tau 0 to tau 1 is an unfolding path in tau 1 to tau 0.
Yes. Yeah. This thing. Yeah. So the picture is that when I'm, let's say this is. I can tell you exactly what, like, since it's a specific example, I can write down what these are. I guess an unfolding, so we define an unfolding sequence. It's a sequence of graphs with these morphisms such that the train track structures are compatible. Yeah. Okay, I think I'm over time. One last sentence I'll say, since this is the random geometry colloquium, is that if I do, so the group out Fn is acting on the space. If I do a random walk in a group, and like, let's say I pick some point X here, and then I apply, if I do that random walk, it converges to some point in the boundary, and that tree is uniquely ergodic, like generically.
What it's saying is that I think this is a phenomenon that happens even in, say, SL3R. So if you look at the random walk on SL3R, it converges to the Thurston boundary, which is G-mod-P, which is not the full visual boundary. So for every two-dimensional, one simplex on the boundary, it picks out its barycenter. And so the collection of barycenters is the part of the boundary where the box converges to line, because that's the direction where there is negative curves and transverse to that there are these flat directions. And in those directions, random walks don't have space to move out too much. So they'll get all concentrated along the negative. Something similar is happening.
Okay. I think I'll stop here.
Any questions? Yeah, so I'm trying to still absorb the state.
Yeah, so sorry, I didn't say much about the our space setting.
So let's see what is the statement here. What you're taking is a sequence of curves. So these are ARIs, it's a R or what? That's just curves, right? And they're basically
three factors.
So they're
Yes.
one.
Yes.
And now we are looking at some RI goes fast enough. So essentially, I see. So I guess the point would be here that you're taking some kind of subsurface projection or some pre-factor projection.
Yes.
And even though you don't have a distance formula, you can still make sense of subsurface projection. That's fine.
Right.
And you're saying that subsurface projection on these pre-factors is growing fast enough. What does growing fast enough mean again?
So for us, it means that the difference of the Ri plus 1 minus Ri goes to infinity.
Okay. And then, so that's fine. But this is.
Sorry? No. Yeah.
Okay. So that's one thing. Then the unfolding part. There exists an unfolding part.
So yeah, maybe the way I stated it is, so our construction is basically we construct an unfolding path.
Yeah. So
yeah.
That is some RI
is the projection of the unfolding path. Yeah.
And its limit set is
an irrational tree. Like downstairs, it's an irrational tree.
Yes, upstairs.
It's the one simplex.
So let's satisfy that part.
Okay. And actually, for free groups, there are two notions of non-uniquely ergodic. Like I talked about length measures. There's also the notion corresponding to currents. And then we get that the tree is also non-uniquely ergodic with respect to that. So we don't know if one implies the other or not.